Hello everyone, my name is Saoirse and I am currently a member of the Bendable Electronics and Sensing Technologies group at the University of Glasgow. It is a pleasure to have the opportunity to share the very first virtual Flex conference with you all. Today, I would also like to share with you the development of a low-cost and disposable graphene oxide Chitosan modified screen-printed carbon electrode for the electrochemical detection of tyrosine. To begin, I would like to quickly outline the work that I will share with you today. I will first provide a further insight into a valuable metabolic biomarker, tyrosine, before discussing the importance of monitoring this non-essential amino acid in biological fluids, and the current drawbacks of the conventional analytical techniques that have been developed for the detection of tyrosine. I would then like to present our proposed solution to the current challenges of tyrosine detection. I will briefly discuss the cost-effective, disposable and biocompatible nature of graphene oxide and Chitosan to explain why they were chosen as suitable nanomaterials for the preparation of the sensitive nanocomposite. I will then explain how the nanocomposite solution was prepared and immobilized on the surface of both a glassy carbon electrode and on the surface of a disposable screen-printed carbon electrode. Finally, I will discuss the electrochemical detection of tyrosine at the surface of each of these electrodes, highlighting the sensitivity and reproducibility of the low-cost and disposable graphene oxide Chitosan sensitive nanocomposite, as well as the effects of scanning speed on the electrochemical detection of tyrosine. Tyrosine is an aromatic amino acid that serves as a building block for several proteins indispensable to human nutrition, and is also responsible for sustaining a positive nitrogen balance. In addition, tyrosine is also an important precursor to a variety of neurotransmitters and hormones, including thyroxine, adrenaline, norepinephrine, dopamine, and melanin. A tyrosine deficiency could therefore induce a variety of congenital or neurodegenerative disease, including, but not limited to, phenylketonuria, cretinism, hypothyroidism, tyrosinemia, and albinism, as well as affecting the balance of dopamine. The continuous detection and quantification of tyrosine in biological fluids would therefore present a valuable platform to aid patients and medical personnel in dietary management and the diagnosis and monitoring of metabolic and neurodegenerative disease. To date, many sophisticated analytical techniques have been developed for the detection of tyrosine and other similar amino acids, including fluorimetry, chromatographic analysis, such as high-performance liquid chromatography, gas chromatography, and ion exchange chromatography, as well as Raman scattering and enzyme-based methods. Although these approaches effectively detect sufficient levels of tyrosine in biological fluids, they are expensive, time-consuming, and require tedious multi-step sample cleanup procedures, as well as expensive assays, special instrumentation, and skilled personnel, eliminating the possibility of point-of-care testing or self-health management. As a result, there is a growing demand for low-cost and sustainable methods for the continuous detection and quantification of tyrosine in biological fluids. By taking advantage of both wearable systems for health monitoring and disposable sensors, it may be possible to design an accurate, rapid, and sensitive method for the determination of tyrosine, and open new opportunities in point-of-care testing and self-health management. In this respect, electrochemical detection methods have gained prominence as a sensitive and selective detection technique for amino acids like tyrosine, due to the advantages of high sensitivity, low cost, easy operation, and real-time response. Furthermore, due to the rapid manufacturing techniques and possibility of miniaturized sensors, screen-printed electrodes represent a facile and low-cost choice for the real-time electrochemical monitoring of biological analytes. Carbon-based electrodes are among the most widely used electrodes in voltammetric analysis, due to their wide potential windows, low electrical resistances, tunable surface, and low cost. Their disposability also makes them attractive from the point of view of sustainable sensors. However, amino acids such as tyrosine provide poor electrochemical response at the surface of solid electrodes, and chemical modification is often needed to improve the performance. Graphene oxide is a promising candidate for the preparation of high-performance electrochemical sensors due to its abundant electroactive oxygen functional groups, large surface area, good chemical stability, low noise, and flexibility. Furthermore, the excellent solubility of graphene oxide in many polar solvents, including water, and versatility of chemical modification are appealing features for the modification of screen-printed carbon electrodes. In addition, graphene oxide nanosheets dispersed in a polymer matrix, such as Chitosan, have exhibited further enhancement in electrochemical performance, ease of immobilization, and biocompatibility. Chitosan is an abundant linear cationic polysaccharide found on the exoskeleton of shellfish. This abundant biopolymer is commonly used to disperse nanomaterials due to its biocompatibility, mechanical strength, good water permeability, and excellent capability of film formation. In addition, the abundance and biocompatibility of Chitosan make this natural polymer an ideal candidate for the development of sustainable and disposable nanocomposites and sensing devices. The current study therefore focused on the development of a low-cost, disposable, and biocompatible electrochemical sensor for tyrosine point-of-care testing, using a graphene oxide Chitosan modified screen-printed carbon electrode, supported by a flexible polyvinyl chloride substrate. The electrochemical behavior of the graphene oxide Chitosan sensitive material that is discussed herein was assessed using both a glassy carbon electrode and the modified screen-printed carbon electrode. The graphene oxide Chitosan modified carbon electrodes were fabricated by successfully immobilizing a homogeneous graphene oxide Chitosan film at the surface of the glassy carbon electrode, which measured 3 mm in diameter, and at the surface of the screen-printed carbon electrode, which measured 1 cm in length and 3 mm in width, following a simple ultrasound-assisted chemical reaction strategy. The homogeneous graphene oxide Chitosan film was first prepared by dissolving a low molecular weight Chitosan powder in an aqueous acetic acid solution. This mixture was then stirred until a homogeneous solution was obtained. Graphene oxide was then added to the dissolved Chitosan solution before sonicating for 5 hours to obtain a homogeneous solution. This homogeneous solution was then uniformly dispersed on the electrode surfaces by drop casting. The graphene oxide Chitosan modified glassy carbon electrode, or the modified screen-printed carbon electrode, were then coupled with a silver-silver chloride reference electrode and a platinum wire counter electrode for the electrochemical detection of tyrosine using an electrochemical workstation. The electrooxidation of 1 to 1000 micromolar of tyrosine dissolved in aqueous hydrochloric acid solutions was first assessed at the surface of the graphene oxide Chitosan glassy carbon electrode in 0.1 molar phosphate buffered saline solution at a pH of 7 using cyclic voltammetry. As seen in Figure 1a, upon the addition of 1 micromolar tyrosine, an oxidation peak with a current density of 8.6 microamps per centimeter squared emerged at 0.78 volts. The oxidation current continued to increase upon the successive addition of tyrosine, with a positive shift in oxidation potential. The statistical analysis of the measured oxidation current that is presented in Figure 1b indicated a linear range of detection from 1 to 1000 micromolar, with a correlation coefficient of 0.9684. The effect of scanning speed on the electrochemical oxidation of tyrosine at the graphene oxide Chitosan glassy carbon electrode surface was studied at various scan rates ranging from 10 to 900 millivolts per second in the presence of 100 micromolar tyrosine. Figure 2a shows an increase in oxidation current with an increase in scan rate and a positive shift in oxidation potential from 0.84 volts to 0.86 volts, which is typical of irreversible diffusion reactions. As can be seen in Figure 2b, the oxidation peak current has a linear relationship with the square root of the scan rate, suggesting diffusion-controlled reaction kinetics. This electrooxidation mechanism was further confirmed by the linear relationship between the logarithm of the applied scan rates and the logarithm of the measured current, as demonstrated in Figure 2c. The linear plot presented a slope value of 0.5679, further indicating a diffusion-controlled mechanism. The repeatability of the graphene oxide Chitosan glassy carbon electrode was also assessed by performing 25 consecutive CV scans in the presence of 100 micromolar tyrosine in 0.1 molar PBS at a scan rate of 50 millivolts per second. As can be seen from Figure 3, the sensor exhibited excellent electrooxidation response for all measurements and demonstrated good reproducibility with a relative standard deviation of 10.69%. Finally, the electrooxidation of tyrosine was examined at the surface of the graphene oxide Chitosan modified screen-printed carbon electrode. Figure 4a shows the CV analysis of 30 to 500 micromolar tyrosine. In the presence of 30 micromolar tyrosine, a prominent oxidation peak was evident at 0.79 volts, similar to the response demonstrated by the graphene oxide Chitosan glassy carbon electrode in the presence of 30 micromolar tyrosine, which shifted to a slightly higher potential of 0.89 volts as the analyte concentration increased. The oxidation peak current also continued to increase with an increase in tyrosine concentration. As can be seen in figure 4b, the measured oxidation current had a linear relationship with the concentration of tyrosine, demonstrating a correlation coefficient of 0.9805. The graphene oxide Chitosan screen-printed carbon electrode also exhibited a high sensitivity of 0.03 microamps per micromolar. To conclude, this work has demonstrated the facile development of a tyrosine point-of-care testing device, based on a low-cost, disposable and biocompatible graphene oxide Chitosan modified screen-printed carbon electrode, supported by a flexible PVC substrate. The graphene oxide screen-printed carbon electrode demonstrated a wide linear range of 30 to 500 micromolar, with a sensitivity of 0.03 microamps per micromolar and good reproducibility. By taking advantage of low-cost, disposable and biocompatible nanomaterials, as well as inert and flexible substrates suitable for wearable systems, this graphene oxide Chitosan screen-printed carbon electrode provides an accurate and sensitive method for the determination of tyrosine, potentially opening new opportunities for point-of-care testing and self-health management. Future work aims to explore the storage stability and selectivity of the graphene oxide Chitosan screen-printed carbon electrode. In addition, the practical feasibility of the sensor in biological fluids, such as sweat, and sensor response under different bending conditions will be explored. With that, I would like to acknowledge the support provided to me by the BEST group at the University of Glasgow, our principal investigator, Professor Ravinder, and last, but by no means least, the financial support offered by the European Commission and Mary Sklodowska-Curie Actions. And of course, a thank you to all of you for your time and attention. If you have any questions, please feel free to ask.